Okay, this video is going to go over solving logs, solving exponentials that have different bases. And we've kind of seen a few things like this. These are a little bit more difficult problems, but we'll kind of talk about it. You've seen so far things like 3 to the 2x equals 9 to the 3x, something like that. And then you say, okay, well, 9 could be written as 3 squared. So 3 squared to the 3x, and then you did your properties of exponents, and since they both had a base of 3, that was great. Nice. So, and then you kind of graduated, and you started moving to problems that look something like 3 to the 2x minus 1 equals 4. Okay. Now, we can't really rewrite 4 to be a base of 3, so we had to end up using logs. And, you went through those videos and but notice over here, the variable was in the exponent, but over here, we just had a constant, so no big deal. Now, we're going to look at problems where the bases are not the same, nor are they multiples of each other, or even powers, I guess. And furthermore, they both have exponents, and inside those exponents are variables. So it's kind of tough. Okay, so what we're going to do is we're going to start off by just kind of converting this into log form, kind of like what we did before. So I'm going to start here with my base. So I have log base 3, and we're going to go around that way. Remember learning that from the other video. And then the argument would be 5 to the 6x equals 2x plus 1. Okay. If you remember from the first video that you heard about the exponent properties, there was a nice exponent property if you have the log of any base of any number raised to an exponent. A Spider-Man rule, but you could take that exponent, bring it down to the front. So the exponent times the log base of that number. It's a nice property of logs that we're going to apply right here. So now I'm going to take this exponent here, use that Spider-Man property, bring it down in front. So 6x times the log base 3 of 5 equals 2x plus 1. And again, I just use this property right here. Okay, so now let's kind of take a look at this. I have 6x times log base 3 of 5. Here is the thing you want to kind of think about with log base 3 of 5. It looks very ugly, but remember, it is just a number. It's just a number. That's it. It's a little bit more than 1. It is a number. So there's no variables or anything, so it's perfect. So it's just like if I had like 6x times 4. 4 is a number. It's the same exact idea. Well, since I don't want to write log base 3 of 5 10,000 times, I'm going to just do something off to the side here. I'm going to let a equal log base 3 of 5. And then whenever I see log base 3 of 5, I'm just going to put a in, and then at the very end, I'll make the substitution. So this thing turns into 6x times a equals 2x plus 1. Okay. Well, now I'm solving for x. And that, by the way, that's an a. That's not a q. That's an a. There we go. Now I'm solving for x. So remember when you had to solve for the indicated variable, get all your x's to one side. So 6x times a minus 2x equals 1. Factor the x out. 6a minus 2 equals 1. Okay. Okay, and now all I have to do, let me give myself a little bit of room here. Okay, now all I have to do is get x by itself. So I'm going to go and divide each side by 6a minus 2. So I'll put it over here. So x equals 1 divided by 6a minus 2. Now, remember, what did a stand for? Well, a was just log base 3 of 5. So x equals 1 over 6 times log base 3 of 5. That's just a number. Parentheses weren't really necessary there, but whatever. And then this whole thing's in the denominator. And there you go. So it's kind of interesting when you think about it. That's that ugly number there. That is the number that made that beginning equation work. Okay? And if you were to take out your calculator and try it out, try typing that in, you will get a decimal. It's around 0.1. Oops, 0.1. Let me draw the points. 0.14. There you go. Okay, it's like 0.147. So basically we're saying, okay, if we come up here in the beginning and you take 0.147 and plug it in for x there and there, that will make the equations equal. It's kind of cool. Now, going one step further, if you think about this graphically, this is some exponential, okay? And we're going to look at the geometry aspect here. This is another exponential. So they're both going to have their curves of what they look like. We want to know when they're equal. So we're looking at their intersection point. Okay, well, let's switch over to Desmos. You see here, there's the first one we were working with. Here's the second one. The first one is the red curve. The second one is the blue curve. And then if you look at their intersection point here, what would you look at that? That's that 0.147. But the real answer, or the exact answer, I guess you could say, was this guy right here. 1 over, don't spoil the fun yet for the next one. Okay. So, okay, try out the problems that were similar to this. Once you get those, then come back for the next more challenging question.